Okay, this problem is much like the last one. We're going to be using the ideal gas law to make this all work. In this case, we are going to have a change in pressure. Everything else will be constant. Well, or is given, which is temperature, basically. Alright, so let's go ahead and write out P specific volume equals RT. Okay? We've got it says there is a change, there's a heat transfer, which is work that's done by changes in temperature. We went over in this in like the first video or something like that. Alright, so we've got a temperature, T1 equals, I'm not even going to write it out because I don't have that much space here. So let's call this is going to be T1. The 300 degrees is going to be T2. Alright, and we want to find the final gauge pressure of the helium, assuming atmospheric pressure is 100 kilopascals. Okay, when we're doing pressure here, we need the absolute pressure. When we're doing the change in pressure, it doesn't matter. The only problem is we've got a delta P that we're trying to find. So we don't know what P is. We do know what R is. That's fine. And T is given. That's fine. But we don't have the specific volume. So first, we have to find the specific volume before we can do anything else. And in order to do that, we need the absolute pressure. Alright, so our given pressure is 10 kilopascals gauge. And what that means is it is 10 kilopascals more than the atmosphere. And the atmosphere is 100 kilopascals. So the absolute pressure is going to be 110 kilopascals times some unknown specific volume equals R. Let's go back to that table we had open. R for helium this time, right? That's what we're looking at, right? Let me make sure. Yeah, this is helium. Alright. Our helium gas constant is 2.0769, excuse me. 2.0769, 2.0769. Let's make sure we're doing the units right. Again, we don't really have anything in energy, so we want it in terms of pressure. So it's going to be kilopascals times meter cubed divided by kilograms times Kelvin. Okay, kilopascals times meters cubed over kilograms times Kelvin. Alright, times the initial temperature, because we're using the initial pressure, we also want to use the initial temperature. That's 100 degrees Celsius. In this case, we're looking at a specific value of temperature, so we do need to convert it to Kelvin. Before we didn't need to because we were looking at a change, and because there's only a constant difference between Kelvin and Celsius, there was no need to worry about the conversion. But in this case, we want to know actually what the Kelvin is. So 100 degrees plus 273. I'm sure you guys can leave without me writing that down. So we got 373 degrees Kelvin. Cancel it out. We know that we're going to divide this by this, so I'm going to go ahead and cancel out the kilopascals as well. And after a little rearranging and calculation, we have our V, and that is going to give us a value of 7.0246. Excuse me, that's not 24. No. 7.0426. And this is going to be meters cubed per kilogram, which is the correct units. Alright, let's go ahead and write that up here, because I'm about to erase all this mess. Give myself a little more space. 7.0426 meters cubed per kilogram. Alright, now let me go ahead and erase this. Okay, so we now have our V value. Now we can go back to this and look at changes. Delta P times V equals, let's make sure that we emphasize that's lowercase, equals R times T. Excuse me, delta T, because we have a change in temperature. Specific volume is not changing because we do not have any mass or volume change. The helium is presumably in a tank or something, so the helium is not going away and the volume of the tank is not changing. At least we're not told that it is, so we're going to assume it's constant. Okay, so in this case, we want the P absolute, but again, the P absolute is related to the gauge pressure by a constant value. So we can say P1 plus 100, you know what, I'm not even going to write it out. Let's just call it P atmosphere minus P2 plus P atmosphere. This is obviously going to cancel out. Times V, which we have up here, equals R. And again, we're going to look at T1 plus 273 minus T2. This should be T2. These are not, I'm not getting my orders right. This should be P1. This should be, that should be P2. This should be P1. This should be T2. This should be T1 plus 273. The 273 is going to cancel out again, so I'm just going to be a lazy bum, and since the final answer is in gauge pressure, then it's actually easier for us to keep this in gauge pressure. So we can determine that P2 minus P1 in gauge, these are both in gauge, that's not a constant, it's just a little subscript, times 7.0426 meters cubed per kilogram equals R. Let's go double check our R again because I forgot it already. Helium is 2.0769. Kilopascals times meters cubed over kilograms times Kelvin. This change here is the same if it's Kelvin or Celsius. We got a 200-degree difference there. T2 300 minus T1 100. I trust you guys can do that. Considering you made it to college and you're studying thermodynamics. Okay. These are going to cancel out because it's all the multiplication and stuff. It's, yeah, anyways. So we got our units down to kilopascals. Alright, so P2 equals, let's get our calculators out.